So in another two videos, we've talked about nucleosynthesis inside of stars. Here, we're going to talk about what happens during supernova events, or supernovae for the plural. So inside of stars, we have reactions where we can take, let's say, beryllium and add helium, and these things will be smashed together to give us carbon-12. We could take this process of making heavier and heavier elements all the way up to iron 56, as we explain in other videos, but the process stops there. What happens is the fusion process runs out of energy. You cannot fuse iron to make heavier elements and still have energy left over. So if we can only make iron elements up to iron inside of stars, how do we make elements that are heavier than iron? So for iron to uranium, iron has the atomic number 26. So we want to make stuff that is large as uranium. We'll just pick 238 as a random example. So if we want to get some from iron 56 up to U238, how would we make all those elements? Well, they will happen during supernova events. So inside of a star, you can imagine a process like this. We have hydrogen and helium and carbon and nitrogen and oxygen, and these are all being fused to make heavier and heavier elements. As they do so, they release a lot of energy, and that energy exerts a thermal pressure that pushes outwards. And that thermal pressure balances a gravitational pressure that would be pushing things inward. So you can imagine a gravitational pressure and thermal pressures that at some point might be perfectly balanced, as they would be inside of the sun. And when they are balanced, then the star has some fixed size. What happens when the star runs out of fuel, if there's no more hydrogen or helium or carbon or oxygen, etc., to burn up, and we're just left with a core of iron, which is the end point, then there's no more thermal force acting outwards, and then the only forces acting are the gravitational forces that are going to be pushing things inwards. And so the star will collapse, and it will do so very rapidly. It'll collapse over a period of seconds or minutes, and as it does collapse, there will be shock waves that will be sending material out, and those shock waves will be very rich in neutrons. Now, the neutrons will be very abundant inside the center of that star. If the star is large enough, we can have neutrons that are formed by this reaction. So let's consider the Bohr model of an atom. We have an electron orbiting around a proton. If the pressures are high enough, that electron and proton can be melded together to give us a neutron. Now, this neutron can be unstable and decay back into a proton and an electron. But inside of a massive enough star, then the electrons and protons will combine to give us neutrons. So you have a very, very neutron-rich environment before that shock wave is created. And so these shock waves will be very, very neutron-rich. Trillions upon trillions upon trillions of neutrons will be pushed out of the star during these shock wave events. And these shock wave events are called supernova, or supernovae for the plural. Now, what will happen to the other elements that are sitting outside here in the wake of that shock wave? Well, they can absorb those neutrons, and that can happen rather rapidly. So we can have a rapid process of neutron absorption. So neutrons will be absorbed rapidly, and that is the so-called R process. Or it can happen slowly, and that would be the S process. And we don't really care about the names for our purposes. Let's just take a look at some examples. Let's say we have iron, and iron 56. Iron has an atomic number of 26. It can absorb one of those neutrons. That naught is for the charge. It would actually have a mass of 1. And that could, these two things can fuse together to give us iron 57. So we still have iron. We haven't created any new elements, but we're going to take iron 56. It's going to absorb a neutron. So the atomic weight will go, the atomic weight will go up by 1. But then iron 57 might have a neutron that decays. So if we have Iron 57, it can decay into cobalt. If it's a neutron, that decays into a proton plus an electron. Then the atomic number will go up by 1, so we'll have an atomic number of 27. That's what will give us the element cobalt. But then a neutron and a proton have the same atomic mass, so we still have an atomic weight of 57. So this will give us cobalt 57 plus a beta particle or an electron that comes out of the nucleus. So you can imagine repeating this process over and over and over again, where we have some element X, and it has an atomic number Z and atomic mass of A. And it can absorb a neutron, and it'll give us the same element with still an atomic mass of Z, but an atomic weight of A plus 1. I should have said atomic number there for an atomic number Z, and an atomic weight that has gone up by 1. But then that same A plus 1 with atomic number Z might be unstable, and it could decay into a new element Y. And so that element Y would be an atomic number of Z plus 1 and still an atomic mass of A plus 1 plus a beta particle or an electron that would be emitted from the nucleus. And you can imagine repeating this process over and over and over again until we generate elements from iron 56 all the way up to uranium, and really any of the actinides, all of the periodic chart from uranium up to the heaviest elements that exist in the periodic chart. From a geology perspective, uranium and thorium are the most important heavy elements to us. When you get much beyond those things have very, very short half-lives and so don't play a huge role in geologic processes. But all of the heavier elements, heavier than iron, would be created by the so-called R or S process, which refers to the rapid or slow absorption of neutrons. That would be this reaction here, and then the kind of decay that would happen in this second reaction here.